Hello, welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about an infection model, a discrete case. So let us consider IN, number of infected population at any time n, and R be the fraction of the infected population who has recovered in time n plus 1. Now, the assumptions are the number of newly infected population are directly proportional to the size of the infected population IN and to the size of the susceptible population n minus IN, where your n is the population size. So, we have an infected population which we denote by IN at any time n. R is the fraction of the population, that is the infected population who has recovered in time n plus 1, and the assumption is that the number of newly infected population, they are directly proportional to IN, that is infected population, and to the size of the susceptible population, that is the population who are vulnerable to catch the disease, is n minus IN, where n is the population size. If you want to model this in discrete case, so I will write that IN plus 1, that is number of infected population at time n plus 1, which is equal to IN, that is the infected population at time n, then the fraction which has been recovered. So, minus R times IN. So, that is the fraction that has been recovered in time n plus 1, and then the newly infected population, and that depends on the law that it is directly proportional to IN, which is this, and to the size of the susceptible population. So, it is a product of IN and n minus IN, and k is your constant of proportionality. So, this becomes a discrete infection model. So, a discrete contagious disease model. Contagious means infectious. So, it is IN plus 1 equal to IN minus R times IN plus k times IN into n minus IN. So, once you get the model, so let me just go through. This is the infected population at time n plus 1, this is the infected population at time n, this is the recovered from the disease which is fraction R, and this is the newly infected population which is directly proportional to IN and n minus IN, k is the constant of proportionality. So, once you get the model, you have to calculate the equilibrium solution. So, you replace IN plus 1 by I star and I replace this here. So, this will give me I star equal to I star minus R times I star plus K times I star n minus I star. So, this and this cancels and you get, if I take I star common, I get n minus I star minus R K times. So, if I take I star common, K times n minus R equal to 0. So, one of the solution is clearly I star equal to 0 and the other is K times n minus I star equal to R. So, n minus I star equal to R by K and I star is equal to n minus R by K. And since this is a population, this should be greater than 0. So, for the existence of this solution, n must be greater than R by K. So, that is the existence condition for the equilibrium solution, the non-zero equilibrium solution. So, we have two equilibria, one is I star equal to 0 and I star equal to n minus R by K, where n is greater than R by K. Now, let us go for the stability analysis. The equilibrium solution. So, for stability analysis, linear stability analysis. So, you have I star is equal to 0 and I star equal to n minus R by K. So, we have the model n I plus 1 equal to I n minus R times I n plus K times I n into n minus I n. So, let we put some function f I is equal to I minus R I plus K times I times n minus I. So, f dash I is going to be 1 minus R plus, if I multiply this, n k minus 2 k I. So, now what we have to do is we have to calculate mod of f dash 0, because your I star one of the value is 0 and you get 1 minus R plus k n modulus of that. If this value is less than 1, then we say that I star equal to 0 is stable about the equilibrium point I star. We say system is stable about I star equal to 0. And then you consider I star equal to n minus R by K. So, you have mod of f dash n minus R by K, which is equal to mod of 1 minus R plus k n minus 2 k, and I is n minus R by K. This gives 1 minus R plus k n minus 2 k n plus 2 R, and if you simplify, this becomes 1 plus R minus k n. So, if this is less than 1, we say the system is stable about I star equal to n minus R by K. Now, let us see the solution numerically. So, once the stability analysis is done, let us find the value of K. So, you have the model I n plus 1 is equal to I n minus r times I n plus k times I n into n minus I n. So, I need to find this value of k, and for this some initial conditions is needed. So, let us take say n equal to 10 to the power 6, r equal to 0.8, and you say 1000 infected in 1 week and 1500 infected in the next week. So, if I put n equal to 0, I get I1 equal to I0 minus R times I0 plus K times I0 multiplied by n minus I0. So, if we consider that 1000 infected in 1 week, say week 0, so your I0 is equal to 1000, and in the next week I1 is equal to 1500. So, if you substitute these values, you will get 1500 here, then it is 1000 minus 0.8 multiplied by 1000 plus k times, I do not know the value of k, 1000, 10 to the power 6 minus 1000. So, I simplify this to get the value of k. So, this is 1500 minus 1000 plus 800 divided by 1000, 10 to the power 6 minus 1000, and that gives you the value of k. So, if you simplify, this gives k equal to 1300 divided by 1000, and this will give 999000. And if you simplify, you will get 0.123451313. So, 1.3013 into 10 to the power minus 6. So, that is the value of k. And if you substitute, so you will get I n plus 1 is equal to I n minus 0.8 times I n plus 1.3 times I n minus 1.3 into 10 to the power minus 6 times I n square. So, I just substitute the value of k, and I got the model in this form. So, the value of r is 0.8, value of n is 10 to the power 6, and value of k is 1.3013 into 10 to the power minus 6. Now, if you recall the stability condition, it says that f dash 0 mod of that is equal to 1 minus r plus k times n. So, if I substitute these values, I get 1 minus 0.8 plus 1. So, approximately take as 1.3 into 10 to the power minus 6, and n is 10 to the power 6. So, this and this cancels each other, and you get 2.3 minus 0.8, and this value will be equal to 1.5, and this is greater than 1. So, for this model, it is not stable at the point I star equal to 0. For I star is equal to n minus r by k. So, I have f dash n minus r by k, and that value we got to be mod of r plus 1 minus k n. So, if I substitute 1 plus 0.8 minus 1.3 into 10 to the power minus 6 into 10 to the power 6. So, I get 1.8 minus 1.3 and it is 0.5, which is less than 1. So, the system is stable about this equilibrium point and it is not stable at the equilibrium point I star equal to 0. Let us now check this numerically. So, I have here already done, but let me generate them again. So, I have n, I have I n plus 1. It starts with 0. This will be 0 plus 1 and I drag it to 30 values. Now, to calculate it, I will follow this law, though I have written 2 more, but I will explain later. So, the value of r is 0.8, the value of k is 1.3013 into 10 to the power minus 6, n is 10 to the power 6. We will talk about this k later. So, it is I n plus 1 is I equal to I n minus r times I n plus k times I n multiplied by n minus I n. So, we will use this to calculate. So, this was 1000, this is equal to I n minus r times again I n. So, r is a constant, I put $sign plus k, this is the value of k, which is again a constant. So, I put a $sign k times I n, which is this value, multiplied by n, which is a constant, minus I n. So, you can see that this value came to be 1500, and you can check from the initial condition for this particular value of k, it has to come 1500, because we have used this value to calculate the value of k. Next, we just generate the values till 30. So, if you get this kind of symbol, it means that there are more digits. All you have to do is come here and double click and you will get the number of digits. So, now I have to plot. I just highlight these up to 30 values, go to insert, take this value and get the value here. So, this is, I can just write here infection model, if I want access title, I click this. So, here it is weeks and here it is population. If you want the grid lines to be removed, go here and just click this grid lines and it will go. So you can see that for this value of r, k and n, you get the model to be stable at n minus r by k. Now, what will happen if I take a different law? So, here the law is, so you can change the laws and you can play with the model. So, here it says that new population will vary directly to the product of in and n minus in. The second one says that it will vary as in square multiplied by 1 minus in divided by n whole square. So, if I calculate this, I will get, this is again a new, so I take this to be 1000. So, under this new law, let us calculate these values. So, this is equal to in minus r, which is a constant, multiplied by in plus k, again a constant, multiplied by in square. So, this in square, open a bracket, 1 minus in divided by n, again a constant, and square. Oops. So, you get some value, you just drag them . So, if I now plot this and this, insert the charts. So, I can see this particular law gives the model going to 0. So, this model is stable about I star equal to 0. Now, if you change anything, this will have effect on the model. For example, say I want to change the value of k. So, let us see how it affect the model. So, suppose I put this as 0.85, let us see what happens. Okay, something weird happens, so 0.6, nothing much, 0.06, 0. Okay. So, it gives the same kind of dynamics even if I change certain values of k. So, like that you can play with the other laws, like here it is given that it varies directly to in into exponential minus log n by n. Let us go back to the slides. So, let us look at the numerical results one more time. So, this is the one we already have seen, that when your model is like this, where the law says that it varies directly to in and in minus in with r value 0.8. This is 1.3 into 10 to the power minus 6 and this is 10 to the power 6. You have seen that the model is stable about the equilibrium point n star minus r by k. This is your I star, and this is the value where it has reached. So, with this model the population will reach a steady value which is equivalent to n minus r by k. So, you can substitute these values and you can easily calculate. Now, this is the model where I have changed the law where it now directly, the new infection directly depends on k times in square multiplied by 1 minus in by n whole square. And we have seen that if we put that with the same initial condition 1000 and the same value of k, please note that this value of k has been taken arbitrarily. If you use some initial condition, this value of k may change. So, it depends on the initial condition whether this particular model will be stable or unstable at the point I star equal to 0. But for this value of k, it is stable about this point I star equal to 0. So, it goes to I star equal to 0. So, with this model and with this rate of recovery, the infectious population will come down to 0. So, everybody will be cured of the disease. Now, where we have the law changes to k times in multiplied by exponential minus in by n. So, in that particular case, I have taken the value of k to be 0.75 and this is the graph which I get. So, it starts with 1000 and with k equal to 0.75, I see that the system is stable about the equilibrium point I star equal to 0. But if I change the value of k to 0.85, I see that the graph rises, that is the infectious population rises. So, it depends on the initial conditions where you will be able to calculate the value of k, whether the system is stable about I star equal to 0 or the system is stable about I star equal to n log k by r. So, what we are doing here is we have the equation I n plus 1 equal to I n minus r I n plus k I n e to the power minus I n divided by n. And we are finding the equilibrium solution of this, for which we put I n plus 1 equal to I n equal to I star. And if we do that, we will get I star, which is equal to I star minus r I star plus k times I star e to the power minus I star divided by n. This I star cancels, and if we take I star common from here, you will get I star minus r plus k e to the power minus I star by n equal to 0. So, this will imply I star equal to 0 and minus r plus k e to the power minus I star by n equal to 0. And this will imply e to the power minus I star by n equal to r by k. This will imply minus I star by n equal to ln r by k. We take this negative sign to this side. So, I star by n equal to minus ln r by k. This implies I star by n equal to ln r by k to the power minus 1, and this becomes ln k by r, and this implies I star equal to n ln k by r. which coincides with this value. So, with this we come to an end of this particular lecture on infectious model for discrete case. In my next lecture, we will take an interesting model, that is a smoking problem or a smoking model. Till then, bye bye.